Good to have you here. This is Unintended Consequences, Episode 3, from May 5th, 2026. Every story we cover starts with someone who had a reasonable plan. In 1921, Thomas Midgley Jr. added tetraethyl lead to gasoline to silence engine knock. He never imagined the additive would raise blood lead levels in entire generations and measurably lower cognitive performance worldwide. Midgley was working in a Dayton, Ohio laboratory on December 9, 1921. He first demonstrated that a few drops of tetraethyl lead in a test engine eliminated the sharp metallic ping that destroyed pistons and wasted fuel. Within 3 years, the same compound was being added to gasoline sold across the United States. It was marketed under the reassuring brand name ethyl. The engineers who championed the additive believed they had solved a mechanical problem that stood in the way of faster, more efficient automobiles. Instead, they created a new, invisible form of pollution that would accumulate in soil, dust, and human bone for most of the 20th century. The problem Midgley and his colleagues at General Motors Research were trying to solve was real and urgent. Early internal combustion engines suffered from knock. This was a spontaneous detonation of the fuel-air mixture. It limited compression ratios. It reduced power. It often cracked cylinder heads. Charles F. Kettering, vice president of research at General Motors and Midgley's boss, had already spent years searching for an anti-knock agent. He wanted American cars to compete with more refined European designs. By 1922, the automobile industry was expanding rapidly. Any improvement in fuel efficiency or engine durability promised large commercial returns. Midgley tested hundreds of compounds. He tried iodine, aniline, selenium, and ethanol. He discovered that tetraethyl lead, a little-known organic compound first synthesized in 1853, worked dramatically at concentrations as low as 1 part per thousand. At the time, lead was already a familiar industrial material used in paint, pipes, and batteries. No one in the laboratory had reason to suspect that dispersing it through exhaust pipes would create a different order of hazard. The decision to pursue lead was therefore a rational, data-driven choice made by competent chemists. They were measured against the performance metrics of 1921 engines, rather than the environmental metrics of later decades. General Motors formed a joint venture with Standard Oil and DuPont to manufacture and distribute the additive. Production of ethyl fluid began in 1923 at a DuPont plant in Deepwater, New Jersey. The first public sales occurred that same year in Dayton and Indianapolis. By 1924, the product was being blended into gasoline at refineries from Bayway, New Jersey to El Segundo, California. Early advertising emphasized smoother engine operation and greater mileage. The word lead was deliberately omitted from pump labels and advertising copy. A handful of public health experts raised alarms almost immediately. In 1922, the U.S. Public Health Service asked for more data. In 1925, a conference convened by the Surgeon General heard testimony that workers at the Bayway refinery had died after inhaling tetraethyl lead fumes. Yet the industry argued that the concentrations reaching the general public would be negligible. Regulators allowed continued sale, provided warning labels were attached to the concentrated fluid itself. Within a decade, virtually every new car sold in the United States ran on leaded gasoline. The practice spread to Europe and Latin America through licensing agreements. The causal chain began with the simple fact that lead burned in an engine emerged as fine particles of lead oxide and lead chloride. These particles remained suspended in exhaust gases. They settled as dust along roadsides and in urban neighborhoods. Tetraethyl lead allowed higher compression ratios. Engines became more powerful and cars more numerous. Annual U.S. gasoline consumption rose from roughly 8 billion gallons in 1925 to more than 50 billion by 1950. This multiplied the total lead released each year. Children absorb the metal through hand-to-mouth contact with contaminated soil. They also absorbed it through inhalation of street dust. Their rapidly growing nervous systems proved especially sensitive. By the late 1950s, average blood lead levels in American children living in cities exceeded 20 micrograms per deciliter. That was 4 times the threshold later judged safe by the Centers for Disease Control. Longitudinal studies begun in the 1970s by Herbert Needleman at Harvard showed consistent dose-dependent reductions in IQ, attention span, and impulse control. Those findings were later replicated in multiple countries. Some econometric analyses have linked the rise and subsequent fall of lead exposure to corresponding shifts in crime rates 2 decades later. The precise magnitude remains debated. A second, less noticed consequence was the masking effect. Because lead improved engine performance, refiners were able to maintain high-octane fuel from lower-quality crude. This delayed investment in catalytic cracking and other cleaner refining technologies. The same chemist who introduced leaded gasoline, Thomas Midgley, later developed dichloro-difluoromethane as a refrigerant. The two inventions together illustrate how a single laboratory's solutions to immediate technical problems could generate long-lived atmospheric and neurological harms. Scientific consensus shifted gradually. Claire Patterson's 1965 paper in Nature demonstrated that industrial lead had increased environmental concentrations by orders of magnitude above natural background levels. The 1970 Clean Air Act gave the Environmental Protection Agency authority to regulate fuel additives. In 1973, the agency announced a phased reduction schedule tied to the introduction of catalytic converters. Those converters were poisoned by lead. Leaded gasoline was fully banned for on-road use in the United States by 1996. Similar phase-outs occurred in Europe during the 1980s and 1990s. They also occurred in most developing countries after 2000 under United Nations guidance. Blood lead levels in U.S. children fell more than 90% between 1976 and 2010. Researchers estimate that the average American child born after 2000 gained between 2 and 5 IQ points relative to earlier cohorts. The phase-out itself created a new, smaller problem. Older vehicles and aircraft that still require leaded fuel continue to emit the metal. Legacy contamination in urban soils remains a localized hazard. No substitute anti-knock additive has matched tetraethyl lead's combination of effectiveness and low cost. That is why small amounts are still permitted in some general aviation gasoline. The leaded gasoline story shows that an additive introduced to solve one narrow engineering constraint can be distributed so widely that its cumulative biological effects become impossible to ignore only after an entire infrastructure has been built around it. It also illustrates the limits of acute toxicity testing when the hazard is chronic, low dose, and dispersed through everyday activity rather than concentrated in factories. Chlorofluorocarbons, in Midgley's case, offer one example. Their unintended consequences appear on a different timescale and in a different environmental compartment. When evaluating any new additive, fuel, or material today, the relevant question is not only whether it works in the engine or the device. The deeper question is whether the total quantity that will ultimately be released has been tested for effects that may take decades to measure in children or in the atmosphere. Consider the current push to introduce new synthetic fuels or battery materials at global scale. Engineers can show clear performance gains in the lab or in a single vehicle. Yet the harder task is to model what happens when billions of devices eventually release those substances into air, soil, or water. Regulators today face the same pressure Midgley's team encountered. They must weigh immediate commercial and mechanical benefits against diffuse, long-term biological costs. The difference is that we now have tools to run those planetary scale tests before widespread adoption. The open issue is whether those tools will be used early enough to prevent another slow accumulation that only becomes visible in the next generation's health data. Fast. That wraps today's case. The lessons travel further when you share them. Send this episode to someone who'd find it useful. We'll see you tomorrow. This podcast is curated by Patrick, but generated using AI voice synthesis of my voice. The primary reason to do this is I unfortunately don't have the time to be consistent with generating all the content and wanted to focus on creating consistent and regular episodes for all the themes that I enjoy, and I hope others do as well.